Some people like to define a closed set as a set that contains all of its limit points, where others like to define a closed set as a set whose complement is open. But it turns out that these two definitions are actually equivalent. Well, how is that true? Well, we'll prove it. Well, how do we prove this equivalence? Well, for any set A, we need to prove that A contains all of its limit points if and only if the complement of A is open, where A is just some set that lives in a metric space E. So A is just any arbitrary set. We can remember A for arbitrary. So let's first prove this direction of the if and only if statement. That is, we're first going to suppose that A contains all of its limit points, and we prove that supposing this to be true, then that means the complement of A is open. And then later, we'll prove that if the complement of A is open, then that implies that A contains all of its limit points. So we need to somehow show that the complement of A is open. Well, how do we show that a set is open? Well, we need to show that for any point in the complement of A, say for any x in the complement of A, that there exists some open ball centered at that point x entirely contained in the complement of A. So, let x be any point in the complement of A, we show that there exists an open ball centered at that x entirely contained in the complement of A. But check out what happens if we were to suppose that this statement was not true. That is, check out what happens if we were to suppose that there does not exist an open ball centered at x entirely contained in the complement of A. So let's see if we can derive some chain of implications that leads us to a contradiction. Well, the first implication that we can make, if we were to suppose that there does not exist an open ball centered at x entirely contained in the complement of A, is that that means that for any open ball centered at x, that open ball centered at x is not a subset of the complement of A. That is, it is not contained in the complement of A. Well, what does it mean, though, for some set B sub x to not be a subset of another set, the complement of A? Well, let's first think about what it means for some set, say, C, to be a subset of another set, say, D. Well, that means that C, this is C right here, is entirely contained in D. That is to say, every point in C is also in D. So, if I want to say that some set C is not a subset of some set D, then that means that there must exist some point in C that's not also in D. There must exist some point in C that's not also in D. Another way of saying this is not every point in C is also in D. So that means that if for every open ball centered at x, that open ball centered at x is not contained in the complement of A, we can say the following. For every open ball centered at x, there exists some point U in that open ball centered at x, such that U is not in the complement of A. But U is just a point in the metric space E. U is just some point in the metric space E, and any point in the metric space E is either in A or not in A. That is to say, it's either in A or in the complement of A. And we've just shown that U is not in the complement of A, so therefore U must be in A. U must be in A. That is to say, U not being in the complement of A, that implies that U is in A. But check this out. This implies that U is a limit point of the set A. It's a limit point of the set A. And you might be asking, well, why is this true? Well, it's directly because of the definition of a limit point. A point X is a limit point of a set A if every open ball centered at x contains a point U in A with U not equal to x. And this is exactly what we have here. We have for every open ball centered at x, there exists a U in that open ball centered at x, such that U is not in the complement of A, therefore U is in A. And we know that U is not equal to x because x is in, by assumption, x is in the complement of A, and U is in A, so U can't possibly be equal to x. So therefore, we've arrived at a contradiction. And the reason we've arrived at a contradiction is because we initially supposed we initially supposed that A contains all of its limit points. And if we were to suppose that the complement of A is not open, then we derived a long chain of implications that eventually arrived at the fact that we were able to find a point X that's not in A, that's also a limit point of A, contradicting the fact that A contains all of its limit points. So therefore, if we were to suppose that A contains all of its limit points, then it must be true that the complement of A is open, because otherwise we would arrive at a contradiction.